you have a system of 10 quasi-linear wave equation coefficients of the metric, then clearly you should expect the Cauchy problem of, first of all, you have an evolution problem, and you should the Cauchy data or initial data should consist of the metric at time 0. So you should expect to prescribe the metric at time 0 and the first derivative, time derivative of the metric at time 0. So that's in a coordinate system, but you'd like to have an invariant formulation that is a formulation which does not depend on coordinates. So then the correct invariant formulation is that this t is equal to 0 corresponds to a 3-dimensional manifold sigma naught. And then g at time 0 is simply the induced metric by g on sigma naught. So here you're going to take sigma naught to be space-like, which means that the metric g naught is Riemannian. And furthermore, the first time derivative of the metric, you can reinterpret it. First, it's going to be a 2 tensor on sigma naught, and you can reinterpret it as the second fundamental form of the embedding. Okay, so in the end, the Cauchy problem consists of a 3-dimensional manifold sigma naught together with a Riemannian metric g naught and a second fundamental form k on it. And you're solving the equation rho alpha beta is equal to 0. And here I'm only going to be interested in a local problem. There are no global issues in this talk, so I'm going to construct a local development of this initial data set in the spirit of the original work of Ivan Choquet-Bruard. And moreover, here what I'm interested in is the regularity of this initial data set. What is the regularity that you have to prescribe on your initial data set sigma naught g naught k, such that you can give a sense to a solution of the Einstein equation? And here you'd like to push the regularity as low as possible. And let me first give you some motivations for looking at this problem in connection to the Einstein equation and in connection of some of the topics we saw in this conference. So I'd like to motivate why you would do this in connection with the weak cosmic censorship conjecture. And it's actually the motivation we had for doing this work. So we already heard about cosmic conjectures. There's a strong one and a weak one. In the talk of Mihalis, he talked about the strong one. Philippe talked a bit about the weak one. So the weak cosmic censorship conjecture, which, by the way, this terminology does not imply that strong implies weak. It's two different conjectures. So it starts with the observation that the Schwarzschild solution contains a singularity. It's a space-time explicit solution of the Einstein equation, which contains an explicit singularity at r is equal to 0. So it's a spherical symmetric space-time. So in spherical coordinates, you have a singularity at r is 0. And obviously, it's a physical theory, and from the point of view of physics, it might be undesirable to have a singularity. You might see it as a limit to the theory. And then the good thing at least about the Schwarzschild space-time is that it's hidden. The singularity is actually hidden by a black hole, so it's hidden to an outside observer. And from that point of view, you're quite happy to say that because it's hidden, you shouldn't see it as a limit to the physical theory. And the conjecture of Penrose, so the weak cosmic censorship conjecture of Penrose from 1969, is that this is actually a generic behavior. It does not only apply to Schwarzschild, it applies to generic spacetimes. I mean, entering from generic initial data. So the vague statement is that singularities are generally hidden by a black hole. And, well, the more precise statement is that for generic asymptotically flat initial data, so let me not say exactly what that means. Essentially, it means that you are asymptotically Euclidean at infinity. For generic asymptotically flat initial data, the maximal Cauchy development of the corresponding solution to Einstein equation has a complete future null infinity. Okay, so if you understand that statement, it's good. If you don't, well, I think this one is already pretty clear. I mean, at least from intuitive point of view. Okay, and here there is one point which is particularly interesting to this talk is this generic here. What does it mean, generic? In particular, in what norm should you measure genericity? Okay, and the reason why it's important is that here you're in infinite dimensions. So of course, the topology depends strongly on the norm you're choosing. And in particular, one point is that obviously, in principle, you see that if you want to make your life easier, you'd like to choose the roughest possible norm for the simple reason that you want your perturbations, so you want to say that for arbitrary small perturbation compared to a specific norm, you can actually, if you have a naked singularity, you can actually cover it with a black hole. But obviously that means that you want your perturbation to be large enough to cover a naked singularity with a black hole. And at the same time, of course, you want this perturbation to be arbitrarily small. So certainly, if you want to have something which is at the same time small and large, you want to go to a rough norm, because the rougher the norm is, the larger it is in a smooth norm. So it's at the same time small in a rough norm and large in a smooth norm. So in some sense, it already points out towards a rough solutions, and in particular, it points towards having to give sense of a rough solution. Okay, so now let me give you an example of a particular celebrated result of Christodoulou where this conjecture has been resolved in the particular case of spherical symmetry. So that's a result from 1999 where Christodoulou shows that weak cosmic censorship holds true in spherical symmetry in the case of Einstein equation coupled with a scalar field. Okay, so you have in spherical symmetry, because of Birkhoff's theorem, you don't have, it's not dynamical. So to reintroduce a dynamical degree of freedom, you have to couple Einstein to a matter field, and the easiest case is a scalar field. Okay, so in this proof, you have two main ingredients. Obviously it's a very long proof, but you could single out two main ingredients, which are, on one hand, precisely a very rough local existence result, and on the other hand, a sharp criterion for the formation of trap surfaces. Okay, and in particular, the point is that to obtain a trap, so in other words, you don't cover your singularity with a black hole, you just show that a trap surface forms before the first singularity. And the way you do this is that you perturb the initial data having a naked singularity with a perturbation which has a jump along the, so in other words, you have the naked singularity. You start with a space-time having a naked singularity at a point, you look at the backward null cone, and then you're going to perturb the singularity. You're going to use a little perturbation which is going to send waves in that direction, and these waves are going to generate a trap surface later on. And it turns out that to be able to generate such trap surface, you need, it is crucial in the proof that you allow for initial data with a jump along the backward null cone. So therefore, clearly, you do need very rough solutions in this setting. It turns out that in some sense they are as rough as you can. These solutions are as rough as it gets. And here, of course, the idea is to try to go towards the non-spherical symmetry case. So you'd like to try to extend both ingredients in the absence of symmetry. And in this talk, I'll be actually only concerned with the first ingredient, which is making sense of very rough solution of the Einstein equation. And here, let me mention that in this result of Christodoulou, because he's in 1+1 dimension due to spherical symmetry, he works at the level of BV. But this is not suitable for higher dimensions, so we'll have to work rather at the level of sober-regularity. Okay, so I hope I convince you that in connection to the Einstein equation, and particularly weak cosmic censorship, it's actually a very important problem to give sense of rough solution. And let me now state the result that I want to talk, which is this so-called bounded L2 curvature theorem. So you start, so again, it's joint work with Klainerman and Rodnianski. So you start with an initial data set sigma naught g naught k. And in terms of regularity, you're going to require that the curvature tensor of your spacetime is in L2, and that the first covariant derivative of the second form is in L2. And then the result is that the Einstein equations are well posed. That is, you can actually make sense of a solution at this level of regularity. And here, well, let me mention that obviously there are some other assumptions to this theorem. You know, in particular, we've heard that you have to satisfy the so-called constraint equations. You have to, in particular, I'm working in the asymptotically flat case. But let me just mention the assumptions that are really limiting here, which are the one regarding regularity. So the curvature tensor in L2, and the first covariant derivative of the second order form in L2. Let me also mention that both of these assumptions are they are both at the same level of regularity. That is, if you look in the coordinate system, then they will both correspond to linear combination of second order derivative of the metric in L2. So you're basically working at the level of H2 for your metric coefficients. It's just a more geometric way of stating the same result. Okay, so it's a well-processed result at the level of H2, but you want rather to state it in this more invariant way. And I'll say more about this in a minute. Okay, so I gave a general motivation for looking at rough solution, but now I'd like to give more precise motivation towards looking at this particular result. So here, first, let me make a connection with previous well-processed result for the Einstein equation. In particular, the previous best known result was the one of Klainerman and Rodnianski in H2 plus epsilon. And there was also an independent result for general quasi-linear wave equation obtained by Smith and Tataru. And in particular here, let me mention that, as I said, we are at the level of H2. And here it's at the level of H2 plus epsilon. So I'd like to mention that it's not about a technical improvement going from H2 plus epsilon to H2. It's really a whole different proof, even both technically and conceptually, for the reason that at the level of H2 plus epsilon, it turns out that the structure of the equation is not so important. In particular, you can give a well-processed result for general quasi-linear wave equations, but when you are at the level of H2, or rather curvature in L2, then suddenly the full nonlinear structure is actually crucial. In particular, there are explicit counterexamples. If you don't have a nice structure, there are explicit counterexamples where well-processed fails in L2, given by Lindblad. So here, in particular, at this level of regularity, you do have to exploit in an essential way the full nonlinear structure, which I'll call null structure, and we heard quite a lot of references to the null structure. So here, this null structure will play also an essential role. Okay, so I'd like also to mention that a nice feature of this statement is, again, the fact that the assumptions are invariant. In other words, you do not need to refer to a particular coordinate system. You can make sense of curvature, the L2 space curvature, or the first covariant derivative of K without any reference to a coordinate system. Okay, so that's important because, as I said in my first slide, remember the Einstein equation are invariant under the choice of diffeomorphism or choice of coordinate system. So you'd like to have a statement which retains this essential feature because you don't want to work in a framework which ties you to a particular coordinate system. Okay, so here, certainly with this statement, this allows you at a later stage, if you work in that framework, to choose any coordinate system you like, simply because it doesn't specify any coordinate system in the first place. And remark, it's not the case, for instance, for the result in H2 plus epsilon. You cannot give an invariant meaning to this. You'll have to prescribe, you'll have to give yourself a coordinate system in which your metric coefficients are in H2 plus epsilon. So in particular, in the work of Klainerman and Rodnianski, they use wave coordinates. And there is a more recent result of Ken Wang, which reproduces this result in the so-called CMC SH gauge. So, I think it's CMC, so constant mean curvature, something harmonic. I don't quite remember the S. But, oh, specially harmonic, yeah, thanks. It's not something, it's specially. Okay. Okay, and I'd like also to make a connection with smooth solution. So I like to mention that this also tells you something about smooth solution, because it's actually, you can rephrase it as a propagation of regularity statement. That is, here you're telling, in essence, that if you start with a smooth solution, the propagation of regularity happens with curvature in L2. So in other words, if I want to make sure that my solution does not develop my smooth solution stays smooth, I just have to check that curvature stays in L2, which is, of course, much easier than having to look at all derivatives. And in particular, it tells you that curvature in L2 is a fundamental quantity controlling singularity formation. And I should say, so these are so-called, this is what is called breakdown criterion. So there were, in particular, this result implies the previous breakdown criterion derived for the Einstein equation by Klainerman, Rodnianski, and later by Arlong and Wang. And in particular, the very nice feature, again, is that it's invariant. So it does not tell you about coordinate singularity, but rather true singularities. Okay, so with the Einstein equation, you want always to distinguish between coordinate singularity, which you're not so interested in, and true singularities. So this, because it's invariant, allows you to talk about true singularities. Okay, and finally, let me talk about the last point, which is, so far I talked about having a simple criteria which is invariant, so which is nice because it's invariant, but here I'd like to discuss whether it's as simple as it gets. Okay, so in other words, in particular, I said it's important that the result of Christodoulou in the BV class for spherical symmetric Einstein model with scalar field is as rough as it gets. So here I'd like to discuss whether there is indeed in this problem, again, some criticality, or whether you think in principle it could go beyond this result. So there is some criticality in this problem, and it's in connection with the so-called econal equation. Maybe write down the econal equation. What's the address? It's here. Okay, so if you, I mean, part of this audience at least is very familiar with geometric optics, and in particular with the econal equation. So the econal equation takes the following form. So here at this stage, assume for a second that the spacetime has been constructed and that you're trying to control this nonlinear transport equation called the econal equation on your spacetime. So g alpha beta, d alpha u, d beta u is equal to 0. Then it turns out, and I'll come back on this later, that the control of this equation requires in a fundamental way that curvature is in L2. So, yeah. In particular, if curvature was not to be in L2. So first of all, it's not enough that it's in L2. You do have to use in a fundamental way the structure of the Einstein equation. But certainly if it was not in L2, then you could not make sense of a solution to the econal equation. So of course you could argue, well, why do you care about this equation? The point is that on a technical level, experts know that any plane wave representation, any wave representation of the wave equation is going to, on a curved background, is going to use this equation as a main building, the solution of this as a main building block. And maybe on a more conceptual level, you can get back all light cones or null hypersurfaces as level sets of these of functions of this type. So as far as light cones are fundamental objects for the Einstein equation and in Lorentzian geometry in general, it's hard to believe you could make sense of the equation without being able to make sense of light cones. Okay, but I still like to say that at this stage it is just a heuristic argument. Of course, it's a very interesting open problem to either go beyond this result or to prove that it's optimal. In both cases, it would be a very interesting result. Okay, so I'd like now to talk about the main strategy for proving these results. So there are 4 main steps. So here, the first step, remember, there is, as I said, here the nonlinear structure, the so-called null structure of the equation is very important. But of course, if you look at which is equal to 0, it's quite mysterious. It's very nice because it's compact, but it's quite mysterious. And again, exactly as in the first slide where we picked a coordinate system to see that we had to deal with an evolution problem, I'd like to pick a coordinate system, or more generally a gauge, which allows me to make this null structure more tractable. And the way you do this is by, so it turns out that coordinate systems don't work, in particular wave coordinates don't work, but you can work in the framework of the Carton for Mills moving frames to recast the Einstein equation as a quasi-linear Young-Mills theory. So what I mean with this is classical Young-Mills theory is well known. It's a seminar. It's a seminar model, hyperbolic system of hyperbolic equations, which is well known to have the null structure. And here you obtain a quasi-linear version of it, which means that instead of having the Young-Mills, the structure of Young-Mills, if you want, on a fixed background, which is the case, the usual case, you get it on a background which is the unknown of the problem itself because it's the solution of the Einstein equation. Okay, so in other words, if you don't know what is classical Young-Mills, it doesn't matter. What you should understand is you get the same structure formally, which is what you care about, but it's on a curved spacetime. So it's on the no, not on the curved spacetime. But I mean, it is on the curved spacetime, but more importantly, the spacetime is not known. So it's quasi-linear in the sense that the background is the unknown of the problem itself. Okay, so the first step is about, if you want, uncovering the null structure. And then once you have uncovered this null structure, you have to exploit it, and that's step number B. But maybe before talking about this, let me give you an equation so that you have something in mind about what is this null structure. So at the end of the day, what you want to do is reduce to a system, and let me just write a scalar version of this system. You want to reduce to equations of the type derivation G of phi is a nonlinearity Q of phi phi. So quadratic nonlinearity in first order derivative of phi. So it's a quadratic nonlinearity in first order derivatives. And as an example of what should be the null structure, you want to see null forms, so-called null forms, and let me give you one of them. So Qij of phi psi would be di phi dj psi minus di psi dj phi. So here you will notice that, of course, for a scalar equation, it does give you 0, but the point is that you have a system. So there are several null forms, but this one is the one that will be relevant to this talk, this Qij null form. Okay, so you can see in particular it has a very specific structure, and there are some cancellations there, which have to be exploited in an essential way. And the way you exploit them is by proving so-called bilinear estimates. Okay, so bilinear estimates, now that you have the structure, you need to exploit it. And bilinear estimates is the correct way to exploit these quadratic nonlinearities with the structure. And here maybe, let me say, just in few words, let me explain what is a bilinear estimate, or rather, let me explain what is not a bilinear estimate, and then I think it will be a bit clear what I mean with this. So let me tell you what is a linear estimate. So I have this wave equation, and let me assume that I want to derive an energy estimate for it. So in particular, if you derive an energy estimate, you'd like to estimate the L2 norm of the right-hand side. Okay, so let me assume that I want to estimate the L2 norm of the right-hand side, and because it's quadratic, let me write it as d phi square. So I want to estimate the L2 norm space-time of this expression, let's say L2 of n. So m is my space-time. I want to estimate this L2 norm. So a linear estimate is an estimate that's going to take the norm of your products and break it in products of the norms. Okay, so an easy case would be, for instance, I think the obvious case you should think of is I'm taking the first one to be L infinity in time, L2 in space. So let's say that you have a time foliation. You have a foliation by a time function. So you have sigma naught, and then you have a further foliation by a time function. And I want to break it in L infinity L2, L infinity time L2 in space, or on the contrary, L2 in time, L infinity in space. Okay, so you get this product estimate, and then you do a linear estimate for each species of this. So for instance, at this stage, you think that you have to deal with the solution of a wave equation. Let's forget it's a nonlinear problem. And then you estimate this. For instance, you would use energy estimate for the wave equation to control L infinity and L2 of the first order derivative. So that would be energy estimate. And for instance, L2 and L infinity, this is typically done with the Strickhardt estimates for the solution of the wave equation. Okay, so here, this estimate, okay, whether it works or not. So first of all, of course, at this level of regularity, the point is that this precisely breaks down. The Strickhardt estimate does not work. But here, you can immediately see that in principle, it cannot work even if you don't know anything about Strickhardt estimates, or well, energy estimate, I guess you know. But if you didn't know about Strickhardt estimate, you know that this estimate fails simply because the way I derive this estimate, a linear estimate by essence, does not use the structure. Whatever the product is here, I will always do the same estimate on the right-hand side. And because the structure is crucial in this problem, as I said, because you cannot expect to close without using the structure, certainly you cannot expect to close with this estimate. Okay, so in other words, you cannot break your product, the norm of the product and product of the norm, and you do have to estimate directly your null form. So your Q of phi, you do have to estimate this in L2 space-time without breaking it in products of the norm, and that's so-called binary estimates, and that's the only way you can actually exploit the structure of the product. If you do this, you lose the structure. Okay, so well, let me not say more about binary estimates, but here let me mention that at this stage, in principle, you have finished. The proof is over here. Here, step A, you uncover the structure. Step B, you exploit it, and therefore you should expect to have finished the proof. There are, however, two main ingredients you need, two black boxes, essentially. You need, and this is needed to prove the binary estimate. So to prove these binary estimates, you need to rely on a representation formula for the wave equation. Think of plane wave representation for the flat wave equation, because it's actually just a slight generalization of this in a curve setting. So you'd like to construct a wave equation. In the curve case, it's not an explicit representation formula. So let me call it a parametrix. So you want to construct a parametrix for the solution of the wave equation on a curve background, elevation g of phi is 0, and you want to obtain the control of this parametrix. So I'll say later what I mean with this. So that's one step. And the other step to prove binary estimates, it turns out that you have two families. They both require the parametrix, but one of them requires an additional ingredient, which is proving sharp L4 Strickhardt estimates for the parametrix. So here, well, let me mention two things. First of all, I call it sharp because you have to prove the same Strickhardt estimate as the one that works for the flat wave equation, except that now you have to to derive it for a wave action on the curved background in a rough setting. So that I call it sharp because you have to prove the same one as in the flat case. And let me also mention that contrary to the endpoint, so-called endpoints Ricard's estimate L2 and L infinity, which does not hold, this one does hold. So that's of course the point is somehow is to find a proof in particular that replaces the wrong Ricard's estimates by the right one. So that's what's happening for some Boolean estimates. Other Boolean estimates, you estimate them directly just using the parametrics. Okay, so here let me also mention that in step B and C, of course, the flat case is well known how to prove Boolean estimates, or even using the parametrics in the flat case. That is, if you're on a flat background in Minkowski, it's well known. Here, the difficulty is to do it on a curved case, where furthermore it's not only curved, it's also rough because you only control curvature L2. Let me also mention in this scheme that step A is essentially algebraic. It's about finding some structure in the problem. But step B, C, and D are about proving estimates. And here, the main constraint when you prove estimates here is just to rely only on L2 bounds on curvature. So let's say you're in the process of a big bootstrap, and the only thing you're able to use within this bootstrap is the a priori these bootstrap assumptions on curvature L2. And finally, let me also emphasize again that if you don't exploit the null structure, you cannot expect to have this result. And in particular, let me mention that it's not only in step B that you exploit the null structure. Turns out that you also need the null structure in particular in step C in connection with this parametrics. Okay, so now I'd like to say a little bit about some ingredients in this proof. So first of all, I'd like to talk about this quasi-linear Young-Mills setting. I mean, the way that how you recast the Einstein equation as a quasi-linear Young-Mills theory. Again, you do not need to know what is Young-Mills. It will just appear on the slide. But the point here is to rephrase the Einstein equation in terms of a connection one form, so that you do see a structure which is totally analogous to Young-Mills, but on a curved background. Okay, so here you introduce. So first of all, you use the Cartan formalism of moving frames. So I'm introducing a general orthonormal frame on my space-time M. It's orthonormal in the sense that G alpha E beta is M alpha beta, where M is the Minkowski metric. And you introduce the connection one form associated to that frame. So in other words, A mu alpha beta is G of D mu E beta E alpha, where here I see this as a one form with respect to mu, with values in matrices. So with respect to alpha beta, this is a matrix, and you can see that it's anti-symmetric because it's an orthonormal frame. Okay. So you have, in other words, you're having a one form, yeah, a mu. I want to see a mu as a one form from. So my connection one form a mu goes from my curved spacetime and ends up in anti-symmetric matrices. So it's the Lie algebra S031. Okay, and that's exactly the setting of Young-Mills. Young-Mills is you're having a connection one form associated to a curvature which starts from a given background. So in Young-Mills, that background would be given. So imagine this is Minkowski. In classical Young-Mills, I would go from Minkowski to a Lie algebra. So for instance, anti-symmetric matrices. So here, of course, the difference will be that we start from a background which is the unknown of the problem itself, and that's why we call it quasi-linear. Okay, so how you recast the Einstein equation? So first recall, of course, that as usual, you have a relation between the curvature tensor and the connection one form, exactly as between the curvature tensor and Christoffel symbols, for instance. Okay, so you have R alpha beta mu nu is equal to d nu a mu alpha beta minus d nu a mu alpha beta, and then you have a quadratic expression in the connections in the connection one form. Okay. And particularly, it has a very special structure, which is the, if you want, the Lie bracket on your metric, on your Lie algebra of anti-symmetric matrices. Okay, so now I need to derive I need to use the Einstein equation somewhere. I mean, of course, this is a general relation, which is always true. So now I need to use the fact that I do satisfy the Einstein equation, and the way you use it is something we already saw, in particular in the talk of Sergiu, is the fact that if you take the Einstein equation, if you take the Bianchi identities and you contract them with respect to one index, you will get divergences of the curvature tensor plus terms which involve the Ricci but because reaches 0 in the Einstein vacuum equations, they vanish. And the only thing which is left from the contracting Gautier identities is this divergence relation, the fact that the curvature tensor is divergence-free. So here I wrote that it's divergence-free with respect to the third index. You have mu here contracted with mu, but it's actually true with respect to any index. Okay, so I'm using this relation, which again is a consequence of the Einstein equation. And then I take d mu on the right-hand side, on both sides here, right and left-hand side, and this equation. You see that on the left-hand side, it vanishes due to this relation. And on the right-hand side, you start seeing, for instance, here you have d mu, which gives you a covariant wave operator. You have d mu of d nu a mu, and here you can commute to get d nu of d mu a mu, which is this term here, which is a space-time gradient of space-time divergence. And then on the left-hand side, you will see the derivative applied to this quadratic term, which gives you this term here. And because I commuted two derivatives here, I see the curvature tensor, which I can express back using this in terms of derivative of a mu. So I get this term here, which is nothing but the term where I commuted derivatives here, and when I replace the curvature tensor by this, plus cubic terms. Plus quadratic terms, which become cubic because you have an additional a. Okay, so here, let me first mention that I'm not going to care about the cubic terms. They do have a special structure, but I don't care because they are lower order in this problem, meaning you can just estimate them using usual Sobolev embedding. But I do care about the structure of the rest here. So here, first of all, this, I claim, is exactly the structure of Young-Mills in a quasi-linear setting. So Young-Mills, if you express it in terms of the connection 1 form, you will see a wave operator, space-time gradient of space-time divergence, and then quadratic term with a very special structure inherited from the Lie bracket of the algebra. So this is exactly what you see here, and that's why we talk about quasi-linear Young-Mills theory, because of course the only difference is that now my background is the unknown of the problem. Okay, so here at this stage, there are two things you want to do. First of all, well, on the left-hand side, there is this term which is a bit annoying here, and which is due to the gauge invariance of the Young-Mills equation. And so that means you want to pick a gauge to kill this term. But at the same time, you'd like to show that this term here has the null structure. And actually, what you're going to do is you're going to do two things at the same time. You're going to pick your gauge such that you kill this term, and it turns out that it will also allow you to uncover the null structure in this term here. I mean, there's a lot of structure, obviously, due to the Lie brackets, but it's not yet in the form of having the null structure, so you still have to do an additional thing here. So here you pick the Coulomb gauge. I mean, there are several gauges, but in particular, Coulomb gauge is very useful. So you pick the Coulomb gauge, dj, aj is equal to 0. So here, j means a space index. Alpha, Greek indices are for space-time indices, j for space indices. So here, j runs from 1 to 3 and corresponds to directions which are tangent to my foliation by time slices. So if you want, I have the sigma t here. J corresponds to the direction which are tangent to sigma t. So in other words, E naught will be the unit normal to sigma t in my frame, and E1, E2, E3 are going to be tangential to sigma t. Okay, so it's adapted. In other words, I take a time foliation which is adapted to my frame. And then, of course, so there are two things that happen. First of all, you kill this term by projecting. So what you can do is you can project on divergence-free vector field due to the Coulomb gauge. That allows you to kill this term because it's a gradient, and projection on divergence-free vector field kills the gradient. And the other thing you need to do is actually to scalarize this equation, because this is a tensorial wave equation. You have the covariant wave operator applied to one form, but what you know how to deal with usually are scalar equations. So you'd like to scalarize your equation. You're going to scalarizing using your frame. But of course, here you see, compared to classical Young-Mills on the flat background, there are two caveats here, which has to do with the fact that you're on a curved background. So neither the scalarization nor the projection divergence-free vector field does commute with the covariant wave operator. Okay, so you get new additional junk terms, and unfortunately, these terms, they turn out to be dangerous in the sense that they are quadratic. So you get a whole new host of terms, and you need to show that they also have the null structure. So in other words, you don't want to destroy what you gain, so you want to show that all these additional commutators with the D'Alembertian do have also the null structure. It's okay. But it turns out that it actually works, and you end up with the following form. So once you have scalarized and projected a divergence-free vector field, you should expect to see a set of a system of scalar wave equations. And here, let me just specify one scalar wave equation for simplicity. So what you see is, so here phi is a projection of my, it's a component of my connection one form. Okay, so I'm scalarizing. So I get wave equation for component of the connection one form. So phi is a component of the connection one form, and you get D'Alembert G of phi is a null form plus lower order term. Okay, so null form is the fact. So what I mean lower order term are these cubic term which I don't care about, and what I mean by null form are these quadratic term which has the null structure. So in particular, these are null q of phi. These are quadratic terms which has this null structure. In particular, it involves these null forms qij, and again, because it's a system, these qij are not trivial because it's a system. Okay, so what do you like to do? Remember, phi is a component of your connection. You want to show that curvature in L2 and connection, one derivative of connection is the curvature. So you want one derivative of the connection in L2. So that means you need to control one derivative of phi in L2, which is just running an energy estimate for the wave equation. So at this stage, I just want to run the energy estimate for this equation. And by running the energy estimate, first of all, because I'm in a curve setting, as I'll discuss, the energy estimate is non-trivial. There is an additional term compared to the flat case which you have to deal with and which is dangerous. And moreover, you also have to estimate the L2 norm spacetime of these null forms, which is exactly what we call bilinear estimates. Okay? So at this stage, you have to control the energy estimate and prove bilinear estimates. Once you have done this, you control a derivative of phi in L2, which is derivative of connection L2, and hence curvature in L2. Okay, so this is the only thing that remains to be done to close the argument. So to prove these bilinear estimates in a quasi-linear setting, again, let me remind you that these are things that are well known in the flat case, but it heavily uses Fourier transform. So here you have to come up with a different proof. So one of the basic ingredients, again, is the fact that you can write phi, you can build a parametrix for phi. That is, you can build a plane wave representation. But of course, in a curve setting, it's only an approximate representation. And I do need to have some kind of exact representation of the solution. So what you do is you use your basic parametrix, and you start iterating an infinite number of times using Duhamel formula, and you build an infinite sequence of terms which are just iteration of the basic parametrics by Duhamel formula. And then this allows you to reduce the bilinear estimate to one of these terms. I mean, it's an absolute convergent sequence. Just have to reduce to one of these terms. They are all similar. And then you can do as if you had only one basic parametric. So that's how you reduce to one basic parametrics. And then, well, you have to do the bilinear estimate for one basic parametrics. And obviously, because you're in the curved and rough setting, you have to come up with obviously different ideas than the usual case. And again, as I said, in these bilinear estimates, there are essentially two families. And one of this family, you also need to, additionally to this, to prove a sharp L4-Strickard's estimate. And finally, there is this business with the control of the energy estimate. So let me mention again that because you're in the curve setting with respect to the flat setting, you get an additional term in the energy estimate, which is from the fact that you're usually when you contract your energy momentum tensor, you use the vector field d by dt in the flat case, which is killing because you have a time symmetry. But in the general case, since you don't have symmetries, you get the deformation tensor of this d by dt vector field, of this generalization of d by dt. And that gives you an additional term, which is trilinear this time, and which, again, is borderline. So you do need to prove that it has a trilinear null structure and to design a corresponding trilinear estimate. Okay? So here, again, once you have done this, you have finished the proof because you are able to control this wave the energy estimate for this wave equation, and that allows you to get L2 bounds for one derivative of the connection, which is L2 bounds for the curvature. Okay? So in the remainder of the talk, let me just explain you a little bit tell you a little bit about this parametrix. And in particular, let me start with a connection of this parametrix to the O'Connell equation, because I'd like also to make some remarks on the O'Connell equation. Okay, so for the rest of the talk, I'll just focus on this step C and try to give you some ideas of this step C, where this is about building a plane wave representation for the wave equation. Okay, so here, at this stage, you can forget about the rest, and we'll just focus on the linear wave equation on a curved background in a rough setting. And we'd like to, we are concerned actually with an old topic which goes back to geometric optics, which is building an approximate formula for the wave equation on a curved background. And of course, so here I have to prescribe initial data. So let's say that phi at time 0, which is here, it's sigma naught. So phi on sigma naught is phi naught. And the derivative of phi, which I'll call t phi, the time derivative of phi, which I'll call t phi in sigma naught, is phi 1, where sigma naught is my initial slice. So you have my initial slice sigma naught. So here I'm prescribing phi naught and phi 1 as initial data of the wave equation. And I'm taking the unit normal t here is just the unit normal future directed to sigma naught. Okay, so it's just the usual Cauchy problem for the flat wave equation, except that now it's on a curved background. Okay, so here what you like to do, first of all, well, it's a plane wave representation, so I need to tell you what is the basic plane wave. So the basic plane wave is ei lambda u tx omega, where here you should, so here tx, don't think of them as coordinates, it's just a point of my spacetime. I don't have coordinates here. But, so these are spacetime variables, and omega and lambda are Fourier variables. Okay, so here, you want to do some Fourier analysis, so you have to introduce some Fourier parameters. And so so of course here, so my Fourier parameters are in R3, and lambda is just the norm of my vector, and omega it's the angle. So you have, so if you want to have psi in R3, and lambda would be the norm of psi, psi, and omega would be psi divided by its norm. Okay, so in particular, omega lives in S2, and lambda is positive. It's a real positive number. Okay, so you'd like, so these are your Fourier variables, and a plane wave, and also, and I'd like to look at what is a good equation for you to satisfy to have a good plane wave representation of the wave equation. Okay, so this is very standard. You apply box G to ei lambda u, and you get two terms. One term is if the first derivative falls on the exponential, and the second one falls again on the exponential, in which case you pick 2 powers of I lambda, which gives you minus lambda square, and then you get g alpha beta d alpha u d beta u. And then the second term is when the first derivative falls on the exponential, but then the second derivative falls back on the same phase, in which case you get only 1 power of lambda, because you hit the exponential only one time. So you get I lambda, and then Dalton g of u. And then, of course, you have the exponential. Okay, so when you see this, in the general case, there are 2 terms, and you're only allowed to kill one of them, so you better kill the most dangerous one. And the most dangerous one is the one in red here, simply because the wave operator cannot recover, does only recover one derivative, and lambda is a frequency parameter, so multiplying by lambda is like taking a derivative here, okay, in Fourier space. So I'm not allowed to take 2 derivatives on the right-hand side of the wave operator because I'm only allowed to recover one. So while this term is fine, this one is dangerous and I need to kill it, and that's why you introduce the solution u of the equinal equation, and this is in particular the reason why we discussed the equinal equation earlier. Okay, so that's something very classical. Actually, I don't know to whom it dates back, but certainly at least from Lax. I mean, Lax used it for his Lax parametrics, but it was probably even earlier, I would think. And so in particular, because I killed this term, you can see that the only term which is left is Dalmatian g of ei lambda u is I lambda Dalmatian g of u ei lambda u, which of course in general is not 0, but in the particular case of Minkowski, so if you're in the flat case, so if you're in R1 plus 3 together with the Minkowski metric, then obviously you can see, I mean, the phase you want to take is u is plus or minus. In that case, you want to take u is plus or minus t plus x dot omega, which is the phase of the standard plane wave equation. And then you can see that indeed, the flat down version of this is 0. And that's why in the flat case, you get an exact solution and not an approximate one. Okay, but again, in general, it's only an approximate solution. 2 Dalmatian g is equal to 0. And of course, what you want to do now that you have one plane wave, you'd like to superpose these plane waves. So in other words, I'd like to take linear combinations of all the possible plane waves so that I'm able to generate any initial data of my wave equation. Okay, see, if I want to approximate this equation, I better be able to generate the initial data. So I'd like to superpose the plane waves, just in the standard way. Okay, so how do you do this? Well, you want to sum, of course, because it's infinite here. You have infinitely many plane waves now. The sum is an integral. First of all, you have this sum over plus and minus, which is the fact that you have 2 choices That's true in the flat case, but also in the curve case. When you solve the inequality equation, you have a priori two choices on the initial slice sigma naught. So that's going to be indexed with plus or minus, with this corresponds to the two half waves of the wave operator. The wave operator is second order, and it does have two half waves. So this sum of a plus minus the two half waves. Then you have the integral over R3, which you write in spherical coordinates. So in particular, you have the spherical. That's the volume element in spherical coordinates. So it's like R squared dr d times the volume on S2. So it's lambda squared d lambda d omega with my variables. And you have this plane wave, ei lambda u plus minus of tx omega. Now you have u plus minus because you have the phases for the two signs here. And then you have the linear combination, the coefficients of the linear combination f plus minus of lambda omega. Okay, so let me first, let me remind you, of course, that u plus minus satisfies the equal equation. And this dependence in the parameter omega, I'd like to make it such that asymptotically on the initial slice sigma naught, u of 0 x omega behaves like x dot omega. So here remark that for the equal equation is a kind of nonlinear transport equation. So in principle, it's not enough to prescribe, it's not enough to prescribe the asymptotic behavior because this is a transport equation. I need to prescribe u plus minus completely on the initial slice. Okay, so I'll discuss this later. But for now, let me say that asymptotically, this is what it should look like. And let me also say that the standard way of doing this is to take exactly u plus minus to be equal to x dot omega, but I'll say later why this choice, which is the one which is always done, usually does not work for us, is not enough. Okay, but of course, for those who are used to the lax parametrics, of course, you are used to taking u is equal to x dot omega in a current system, but this is not something we can do, and I'll explain it later. Okay, so here, let me give you what you get in the flat case, because for those maybe who are not used to this, you will recognize that you know these parametrics very well. It's just the plane wave parametrics. So in the flat case, this is your phase. And then you can get explicitly this f plus minus. You can relate them to initial data by Fourier transform, because in the flat case, you just take exactly this to be x dot omega, and you get the phase of the inverse Fourier transform, in which case f plus minus of lambda omega by a simple computation just given by 1/2 of the Fourier transform phi 0 hat of lambda omega, so the Fourier transform on R3, minus or plus I over lambda phi 1 hat of lambda omega. Okay, so it's a completely straightforward computation. It's just because your parametrics at initial time, in the flat case, is just the inverse Fourier transform. So you can explicitly relate f plus minus to the Fourier transform of the initial data. Okay, so you recognize, obviously, that in the flat case, this is just the plane wave representation. In the curve case, again, this turns out to be just the so-called lax parametrics of geometric optics, where, for the experts, you know that there's also a symbol which satisfies an infinite number of transport equations, but at the level of regularity where we are, we can only make sense of the most fundamental building block of the lax parametrics, which is this ei lambda u, where u satisfies the equal equation. Okay, so now there are two steps. There's a construction step and a control step. So let me tell you what this means. The construction step is the fact that, you want to be able to generate all initial data to the wave equation. So that's precisely why you chose this behavior at infinity asymptotically on sigma naught. And that's why you have this freedom of choosing f plus minus. But now you need to say that this is enough to be able to generate the initial data. So that's the construction step, which tells you that, indeed, if there does exist a choice of f plus minus, which obviously you will prove also that it's unique, but at least you need it to exist, such that s at time 0 coincides with phi naught, and ts at time 0 coincides with phi 1. So your parametrics does generate all initial data of the wave equation. And furthermore, of course, it's not enough. You need this f plus minus to satisfy the sharp estimate, which is true in flat case. For instance, if you look at my formula here, if I use Plancherel, obviously I will get the estimate which is exactly written here with an equality instead of an inequality. But here what is important is to get this inequality here, to relate the size of f plus minus. So this is very natural, because here I'm having essentially the h1 dot norm of my initial data. On the Fourier side, you should expect to have lambda to multiply by lambda times f plus minus and estimating R2. Okay? And then you have the control. So the control is the fact that your parametrix is only an approximate representation formula. So in particular, it only satisfies the following. It satisfies the inversion G of S is not 0, but rather it's equal to an error term, which I'm going to specify immediately. And then, again, S on sigma naught is phi naught. That's from the previous step. And TS on sigma naught is equal to phi 1. OK? So what's happening here is that, again, when you apply the inversion G to S, you don't get 0, as we saw in the previous slide. You pick up I times the inversion G of U plus minus, and your lambda squared because of lambda cube, because you get an addition power of lambda. So you see that you don't have an exact solution. But if you want to control your parametrics, you see from there that you just have to run an energy estimate this time for the parametrics. Okay, if I can close this energy estimate, provided I can close this energy estimate, to control the parametrics, I simply need to control this guy here in L2. Right? If I control this in L2 space-time, using the energy estimate, I will control the parametrics. And it turns out that the estimate that you have to prove is the following one. You want to control the L2 norm space-time of the error term, again, by the H1 dot norm of your initial data, which is lambda f plus in L2 plus lambda f minus in L2. So here I should mention that this estimate is the sharp one. If I had a smooth symbol, I'm in a very rough setting, but if I had smooth symbol, I mean, a smooth, if the phase y was the flat phase minus plus t plus x dot omega, and if this was a smooth symbol, this would be the sharp estimate that you have to prove. Okay, so I guess I have 5 more minutes, maybe. Maybe 3, but I think we started a bit late. Okay, let me try it. Okay, anyway, I'll finish with a slide on remarks. Okay, so so first of all, again, the main constraint is to also do this step, only assuming L2 bounds on curvature. So here, I'd like to make some remarks, first of all, with respect to regularity with respect to omega, because obviously the econal equation, you expect limited regularity because if you start differentiating, you have G here, so you will start seeing the curvature tensor if you differentiate with respect to space-time variables. So you expect to take at most 2 derivatives of this equation. But in terms of omega derivatives, in principle, it's just a parameter, this omega, but the metric, the space-time, has nothing to do with this omega. So in particular, the metric is independent of omega, so you could expect to be able to differentiate as much as you want in omega, in which case you would get C infinity in omega, and that would make your life much easier. The point is that it's not the case because the econal equation is a transport equation, and as any transport equation, you get more regularity in the direction of transport. And here it's a nonlinear transport equation. So when you start differentiating in omega, this direction of transport, it starts rotating because it depends on the parameter omega, and therefore you exchange a good derivative against a bad one, and that's where you start losing derivative. So in other words, the fact that you have better derivative in the direction of the transport kills you here because the transport is nonlinear, so it depends on this parameter omega. Okay, so that's one thing. Another thing is the choice. I talked about the choice of u at time 0. So again, 100% of the time for lax parametrics, I mean the so-called lax parametrics, you would choose u plus minus times 0 to be x dot omega. Here, I'd like to mention that this is not allowed. This would, at this level of regularity, this is just not allowed. You can't do that. And you have to do a more geometric choice, which turns out to be related to mean curvature flow, which allows you to squeeze as much regularity as possible, respect both to x and omega. I'd like also to mention the fact that, to go back to this issue of minimality of the curvature tensor in L2. So curvature tensor in L2 is minimal, as I said, to control the econal equation. And this is actually related to the radius of injectivity of the level surfaces of U. This is because the econal equation is a scalar transport equation. So you can just integrate it using the so-called method of characteristics. And your characteristics in this problem are just null geodesics of the space-time. So you know very well for the method of characteristics that what you need to make sure is that the characteristics do not cross, otherwise you get a caustic. So you want to prevent caustic from forming, and it turns out that this caustic, as they are related to the radius of injectivity, you need to get a lower bound on the radius of injectivity for these null level hypersurfaces of U. And it turns out that curvature in L2 turns out to be minimal for that estimate. Okay, so it is for this reason that curvature in L2 is minimal to control the econal equation, is just to control the radius of injectivity of null hypersurfaces. And finally, let me finish by saying that even with these precautions, even with extracting as much regularity as you can with the econal equation, you still are able to get very little out of it because of the limited regularity. And that still needs to be enough to control your error term, for instance, which is a Fourier integral operator with phase u and Siebold diversion g of u. And as you know from standard method, from classical proofs such as tt star and t star t arguments, you have to integrate by parts lots of times, which is not allowed here. So here you have to come up with a different proof, which is much more cautious in terms of what regularity is needed to close the argument. Okay, well, I'll stop here. Thank you.